Okay, I think we're recording. You are looking at my barn, or a part of my barn, and I have a whiteboard here I've cleaned off, and I'm going to back up. I'm using the computer's camera, so it's kind of wide angle here, a little close. I'm going to do the Wednesday lecture this way. I'm going to try to stream Friday morning's lecture this way. I'll put some stuff out on Canvas on that. But I'm going to do projectile motion problems on the board. Okay? So look in the Canvas instructions. It'll tell you about when this is due and everything. Try to, if you can, watch this before the Friday class. But if you don't, it's understandable. This is getting there late. We're doing what we can. Okay? So 4.2. Projectile motion. And let me try to use black and blue because I don't know how well you can see that. So projectile motion. Now projectiles moves only under the influence of gravity. And I think you can see that. I'll try to write it a little bigger, getting this figured out as we go. Projectiles can be, some examples, basketballs, as you saw in the lab, that you hopefully completed. You can have bullets. You can have rockets. Can be projectiles, definitely, when the motor's not working and everything else isn't. People. When you're diving, that can be considered a projectile. When you're jumping on a trampoline, neglecting air resistance, it's a projectile. Only when gravity is influencing. If you got a jetpack, you're not a projectile. A mortar round that's not assisted could be considered a projectile. Not a mortar board. I guess you throw your mortar boards at graduation, then you have a projectile mortar board. They don't blow up. They better not anyway. So those are just some examples of projectiles. Now the key when you deal with projectiles is gravity only influences, and I talked a little bit about this the previous class, in the negative y, should say y direction. I don't have good sheen on this board, so I'll probably have to stop and start when I clean it because I have to use acetone on it. So there's no influences in the x direction. Remember, we're assuming no air resistance. No air resistance. So with no air resistance, then it's not going to have anything to project it. It's just going to keep on doing what it's doing in the x direction there. Okay? So that's projectile motion. So if that's true, what I'm going to say is, what you want to do is you want to break down motion into x and y movement separably. You want to separate out x and do x. It's x motion here, y motion there. And I'll do an example here in a minute. We'll try to get two examples in to show this. Okay? So, normally when you have projectile motion, you initially need to know how fast it's going. They'll give you an initial velocity, or maybe they won't. You have to work your way back to it. But if you think about it, let's have a cannon shooting a person out of it or something. Okay, so we've got a cannon here. And let me just have it there. So this cannon shoots a person, and this is blue, so blue, 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 down into the water. All right, so the guy got tired of just jumped cliff diving, so he went cannonball. I guess when he hit the ground, he had to do a cannonball. Yeah, see, I can do humor in the barn, and under this COVID crap. All right, so there's a diver going out, made a cannonball. I didn't do that nice and parabolic. If I did it really good and parabolic, it would look something like that. But you get the gist of it. Hopefully. So nice parabola there. Look, if you know math, when you see the equations, you'll know what's parabola. X and Y motion. Now, what's going on in the very beginning? There's your initial velocity. That's a vector. And last time we said we could break vectors down into X and Y components. So if I can break vectors down into their components, why can't I break down the cannon, the guy shooting out of the cannon, into an X motion, into a Y motion? So let me get a little visual aid to help you there. All right, so you see the rocket I got here, right? Okay, so initially the guy's up at an angle like this, all right? But he's going off that direction, right? That direction. But you can break down that motion into only horizontal motion. And vertical motion. Oops, hit the second story of the barn there, where they used to keep the hay. I just keep storage right there. Now, vertical motion, horizontal motion from an initial velocity at some angle. Okay? Put down the visual aid now. And let me find what I did with the other motors. I'll just use the green. So that means if I break this down, I have some initial velocity in X and some initial velocity in Y. Okay. Now, there's some angle there. I'll call that theta. Some angle theta. Had it in my back pocket. Forgot about it. Got so excited with the rocket. Now, let's find these X and Y components in terms of the initial velocity at some angle and theta. So if you remember from last lecture and you read your previous notes before you started watching the video, like you always should, because you need to know what we just did because it's a continuation. So you would know then that we could say that the X component of the initial velocity is just, and remember I said X component is cosine, Y component is sine, as long as we base the angle off the X-axis there. So then we can just say then that's V sub I cosine of theta, and then the Y component is going to be V sub I sine of theta. Okay. This we will use to solve these projectile motion type problems. Okay? This is kind of our jumping off point, our starting point when we solve these problems. You find the initial velocity in X, initial velocity in Y as best you can, and then use that to continue doing these problems. Of course, list your knowns and unknowns, draw a picture, and let's go look at an example. So I'm going to turn the video off for a minute, clean, and